Okay, good morning. Welcome back to the final day of this summer school and in preparation for tomorrow's workshop day. So yesterday we started talking about data streams, sketching techniques, and brought in these other techniques like Chebyshev inequality, Markov inequality, and Chernoff bounds. And we looked at things like count-min sketch, AMS sketch, and how these can be analysed using these tools. So what I want to do today is sort of jump into a few different topics. I'm going to start off by talking about F0, or count distinct, and connect that up with Chaim's talk yesterday, and then just pick a few more topics out of the possible slides that we have to play with. Okay, so we said these frequency moments, Fk, are things that you get by looking at sums of powers of values in a vector, and F0 is this quantity which is shorthand for the number of distinct items that we observe. So yesterday Chaim was talking about how we can do this coordinated sampling, and then we can use the hash values that we observe to generate that coordinated sample to also estimate the number of elements that meet a particular criterion. And that analysis was done with the assumption of fully independent hash functions. So what I'm going to do here is sort of essentially look at the same underlying algorithm and analyse it using the tools that we have to estimate the number of distinct values under limited independence. Okay. So this idea of k-minimum values has appeared in a number of places. I'm going to follow the outline of Ziv Bar Yosef and others from about 2001, I think it was. To analyse this algorithm for estimating number of distinct elements. So here's the picture. We have some number of distinct elements arriving, drawn from a finite domain. So let's let M be the size of this domain, and what we're interested in is F0, or I'll also refer to this as N, as the number of distinct elements within this domain. And the algorithm is basically the one we saw yesterday. We're going to have a hash function. That hash function is going to map each stream element somewhere into some range. I'm just defining this range as capital R. Sometimes it's convenient to think of R as the range 0 to 1. Sometimes it's convenient to think of R as just a large integer. So we're going to be using a large integer interpretation, but we can kind of map that back to 0 to 1 just divided by R. And we're going to track what happens as we map elements under this hash function. So what we do, we pick our hash functions. It's going to be pairwise, two-wise independent. We're going to map onto a large R, large enough that we ensure we don't have any collisions, so we don't worry about those. Essentially, with only very vanishingly small probability we have collisions, so we can just condition on no collisions and continue. And we do what Chaim said yesterday, right? We hash every element, and we're going to keep track of k elements that achieve the k smallest hash values. All right, so I've switched here from k to t, it would seem. Okay, so for each element in the stream, we compute its hash value, and then we'll track the t distinct items achieving those smallest values of the hash. And the important thing to realise here is this is where the power comes from in counting distinct elements. It's the very simple fact that because we fixed the hash function, we see the same element many times. That hash function is fixed, so it gets mapped to the same location, so we don't overcount. Right. So this is sort of the one piece of technology that ensures we're only going to be looking at the number of distinct elements rather than the cardinality of the multiset. So for our analysis, what we need to do is reason about Vt being the smallest distinct value of the hash function we've seen, and you can kind of see how this maps to what Chaim was saying yesterday about sort of looking at that k smallest or k plus first smallest hash value. So this is how it looks with the picture. I'm going to pick here just the two smallest values. So initially, I see an element, I see another element, and so I keep track of, well, what is the second smallest hash value? I see some other elements, and so I drop down. Another element comes, but this is above the tth smallest hash value, so I don't need to update anything. Another copy of an element I've seen before comes, nothing changes. Some new element comes below, and I go down further. And again, what's the intuition behind this algorithm? It's simply that this hash function is behaving, reasonably close to uniform. Then I should expect a uniform fraction. I should expect sort of the k elements with the smallest hash values to achieve a roughly k over m fraction of the domain when I hash them. Right? So this VT should be a roughly k over, sorry, in this case, yeah, k over m fraction of this range. Right? Things are uniform, that's exactly what I get. So what I'll do is I'll use this hash value to build my estimator. In this case, we actually build a relatively naive estimator that just says estimate f0, estimate n or f0, the number of distinct elements, by looking at the reciprocal of this hash value. So it's sort of look at the fraction of the range that this hash value occupies, Vt over R, take the reciprocal of that, and multiply that up by t. So it's saying if t elements occupy this range, if I sort of extrapolate that linearly, how many elements do I think I have in total? Hopefully that algorithm is clear. It's the second time we've seen basically this outline. So we can kind of believe this algorithm works because it seems plausible. But we want to prove that it works, so we're going to essentially follow the outline that we built yesterday in terms of reasoning about the output of the algorithm as a randomized event, looking at the probability that we get a good estimate, and then try to amplify that success probability. So what we can do is just say, well, let's assume things go well for us. Let's assume we have a good estimate. Well, what could go wrong? What could go wrong is if that estimate is either too high or too low. And what would it mean for the estimate to be too high? It would say that we have too many items hashing in this low end of the range. So we see too many items with a small hash value. Right? So that would push up our estimate of f0. So what we can do is say, well, notionally there is some sort of correct upper bound on where Vt should be in order to give a good estimate. Right? We could say, well, if we knew f0, and we know all these other parameters r and t, then there's sort of an upper limit of where Vt should be that would still give us an estimate that was within, say, a 1 plus epsilon factor of the true answer. So what we'll do is we'll say we'll fix that upper limit, and we're going to have a bad estimate if we have too many elements hashing below that upper limit. Right? We have more than t elements hashing there. And that's an event that we can then start reasoning about. Right? So we say, well, for our input S, we get this bad event, we get a too high estimate if we have more than t elements whose hash value is below this sort of critical threshold. And the reason we write this like this is because we can then sort of say, let's just look at each element individually and say what's the probability that it hashes below this range. We'll say that for each element individually, it's slightly unlikely to hash too low. And so, by the fact that we're repeating this for many elements, we're going to be very unlucky if so many of them hash to a low value. Right. So what mostly follows then is algebra rearrangement, figuring out how to bound things in a reasonable way. Right. So for example, we have some expression here for this critical threshold value that has a 1 plus epsilon on the bottom. That's slightly inconvenient to work with. So we just sort of say that 1 plus epsilon, a factor of 1 over 1 plus epsilon is roughly like a factor of 1 minus epsilon. And then we make that precise by saying, well, it's upper bounded by a factor of 1 minus epsilon over 2. So, just simple algebraic rearrangement. And then the next step is to say, well, what's the probability that we get something hashing in this range? We have a pairwise independent hash function, so we can say, well, probability that we hash into that range is just essentially the size of the range over the size of the total number of possibilities, right? And so we can sort of say, we can essentially translate this parameter here, the fraction of the range, directly into a probability. Okay, so we have this probability that any element hashes into that range. And I'm actually simplifying things a little bit here. There are some rounding issues because we're going into an integral range rather than a fully continuous range. But again, these are sort of things that, so when you do the first analysis, you kind of ignore them, and then when you do the final analysis to write it up for a paper, you kind of have to fill in all those little details. Okay. So then what we can do is use that tool, use the Chebyshev inequality to let us reason about how likely is it that we'll get many items hashing into this range. So again, we'll set up a random variable y to count the number of items that hash in this range. Look at the expectation of that variable and say, right, we don't actually expect that we'll have too many items hashing in this range, right? We shouldn't have too many. So we're going to be unlucky if we have much more than this. So let's look at the variance of this event. And here again is where we need to sort of dive into actually properties of the hash functions to make everything work for us, right? So what we need to first say is that for any individual item I, we can look at what's the variance of the event associated with that item hashing into this range. That's straightforward because we have a probability, so it's just p times 1 minus p. And then we say, well, what's this event y is sort of the summation of all those individual events. If everything is fully independent, then we know that we can get sort of the variance of sum just by summing up the variances. But actually, we don't need full independence. We only need to say that these pairs of events are independent. And we get the pairwise independence of events from the fact that we have these hash functions that are pairwise independent. So, after a while, you're going to get used to the shorthand that you can sum expectations and variances of things derived from pairwise independent variables, just because you're only looking at sort of first and second moments as a rough guide. So then what we can say is, okay, let's look at the overall variance of this variable y, the summation of all these elements, and that we can express in terms of summing up these probabilities. And actually, we can kind of just round things up quite a lot. All we really need here is that the variance of y is less than this parameter t. And now we plug in the Chebyshev inequality. We say, what's the probability that we have more than t elements hashing into this range? It's the probability that y minus its expectation is more than some sort of small fraction epsilon times t. We say, what's the probability that we get sort of slightly more epsilon t more things than we expect? We can plug in that what we then need is just the variance of y divided by sort of the square of that value. And because we have the variance depending on t, we can just choose this parameter t large enough to make this probability go down to a constant. Right? So if I was doing this with just t equals 1, I'd be unlucky quite often. I'd get 2 or 3 elements quite a lot of the time. But as I increase t, I've got concentration happening. I'm less likely to be far from my expectation. So because we have the freedom to set this parameter t, we'll set t proportional to 1 over epsilon squared. That's going to make that probability of that event smaller than a constant. Okay, so what that said was we can use this outline of looking at random events defined based on the algorithm, analysing them under properties of the hash function using Chebyshev inequality to show that, in this case, the probability of being a little bit above our target value, making an overestimate, is no bigger than a constant. So then we want to do the symmetric side and say, well, the probability of an underestimate is also no bigger than a constant. And it's not going to be surprising to you that you follow essentially the same outline. So just your inequalities are looking at sort of smaller values rather than larger values. But essentially you follow the same kind of algebraic manipulation to get to events that you can reason about using Chebyshev inequality.
What? So
I'll have to look at the slides carefully. I know we've proved one direction. Yeah. The estimate to be too high. I think you may be right. You know, we basically put up two thresholds. We say we shouldn't have too many elements beneath one threshold, too few elements beneath the other threshold. So the outline is correct, and I'll check the details afterwards. Right. Okay. So what we end up doing is we sort of analyze these two events. We analyze the event that we get an overestimate, and we analyze the event we get an underestimate. We show in both cases we have a smaller than constant, say smaller than a fifth probability of those outcomes. And then you can say, okay, just by union bound, then the probability that neither of those happen is, say, at least 3/5. So again, we have a greater than half probability of seeing something which is good. And then again, we can kind of invoke that same trick we had before. We can invoke the Chernoff bound argument that said, well, once we have one estimator which is good with slightly more than half probability, we can repeat this estimate many times, take the median of those estimates using independent random values, using independent hash functions, the one we used before, and argue that we're unlikely when we look at the median to end up with a bad value. So what happens when you kind of put that all together? What does it say? Well, the important thing in that analysis was this setting of the parameter t. It said, well, how many different hash values do you need to keep around for this to work? And that t was dependent on 1 over epsilon squared. And then the total space in bits is 1 over epsilon squared times, let's say, the hash value, the size of the hash values that you're keeping. Those hash values fall into a range proportional to a polynomial in m. So you need logarithmic in m bits. So it was saying you can do this using number of bits that looks like 1 over epsilon squared times log m. And you may be unsatisfied with that. You may say, well, is that really the best we can do? Can we sort of squeeze this lower? And the answer is yes, you can squeeze it a bit lower. So with some additional hashing tricks that I won't go into, you can get that down to 1 over epsilon squared plus logarithmic in m. And the time cost, the actual cost to actually run this algorithm on a large amount of streaming data is pretty cheap, right? Because all you're doing in each instance of the algorithm is evaluating a very cheap hash function and keeping track of the k-smallest values, which you can do using a heap or using some other fancy data structure. So pretty efficient to actually run this. Okay. So this is actually something people care about. Counting the number of distinct elements in a sequence is something that's been used and implemented in a variety of places, from search engines like Google tracking how many different users do they have, other organizations on the internet tracking how many different customers are accessing their services and so on. And so there's some interest in saying, well, how do we really kind of take this kind of algorithm and engineer it into the best implementation? And I think what's generally recognized as the best implementation of this whole class of count distinct algorithms is this hyperlog algorithm due to Flageolet and others. And when you first look at this algorithm, it looks sort of quite different in nature. But I'm going to argue that sort of underlying it are the same kind of intuitions, but just with a different implementation and a much more technical, involved analysis. So the way the hyperlog algorithm works, it also uses hashing, as you'd expect. Again, you apply a hash function to an element so that every time you see the same element, you're going to make the same decisions, so that then you can stop worrying about repetitions and just worry about what's going on with the supporting set. So what the hyperlog algorithm does is it sort of does hashing to a number of buckets, and this sort of number of buckets is again going to depend on 1 over epsilon squared. And intuitively, why you hash into a number of buckets? It's so that instead of doing repetition to bring variances down, you're using averaging via a hash function to bring the variance down. And so within each bucket, rather than keep track of the k minimum values, you're keeping something which is really depending just on the one minimum value in that bucket. But instead of explicitly keeping what is the minimum value you see in that bucket, you keep this kind of derived quantity, which is you take the hash value, you take the logarithm of that and sort of look at the floor of that value, and you look at what's the largest value of that floor of a log of anything that you see hashing into that bucket. And again, this seems kind of unintuitive. What's this really doing? Well, this sort of floor of log is really telling you what's the most significant bit in this hash value. And that value of the most significant bit you can kind of see as a very coarsened version of the actual hash value. Right? You're only keeping some information about the hash value up to the sort of most significant bit, sorry, of the hash value you see, rather. So you're losing information, but you're doing it sort of many times because of this 1 over epsilon squared y's division. So what you're going to do is you're going to sort of get a very crude estimator for each bucket, but you've got enough buckets, you're going to get precision back from those. And the reason for doing all this is that to keep this location of the most significant bit of the hash value, you only need log of m bits. Right? You need log m bits to actually keep the hash value, but now you're just keeping the index of the most significant bit. So you need log bits. And for all practical purposes, this is 5 or 6 bits.
It also has the advantage that you only compute one hash function for each key.
Yes. Yeah,
That should be major.
Exactly. Yeah. So you know, this is combining all the things, right? It's fast and compact, which is probably the motto of this summer school. So that lets you count the number of distinct elements. This is not the only thing you'd want to do. If all you wanted to do in life was count the number of distinct elements, then you could certainly run these algorithms, but you know, you wouldn't really learn very much. So the other thing you might want to do is sort of similar to what Hein was saying. You might want to start saying, well, what about subsets? Can I learn something about subsets? Can I learn something about combinations of sets? So in particular, using this kind of hyperlog algorithm, you can start making some estimators for things like, well, what's the intersection of two sets? So suppose, you know, I have a hyperlog summary for how many distinct users did I see visiting my online store X, how many distinct visitors visited my online store Y, can I estimate how many visited both?
What is K and V?
K minimum values. So this algorithm, well, this really is a class of algorithms that track hash values and keep the k smallest ones, k minimum values, bottom k, many names. Okay. So, you know, we might want to look at, say, what's the size of the intersection between two sets. Well, if we have a summary of each one, then again we can start playing a few little tricks. So with hyperlog, we lose the ability to sort of directly do these intersections and in the way that you can with the k minimum values summary. But what you can do instead is you can certainly merge two summaries together by going through every bucket built with the same hash function and just taking the max of each pair of buckets to get a summary of the union of those two inputs. So you can estimate the cardinality of set A, you can estimate the cardinality of set B, subtract the cardinality of the union of those two sets to get some estimate for the intersection of those two. It's not going to be perfect. I mean, things like intersections are fundamentally hard things to do in small amounts of space. But what you can do is get some error that scales, in this case, I think, the square root of the product of the set sizes. So when the intersection is very small, unsurprisingly, you're unlikely to be able to really accurately determine the size of it. If it's sort of moderately large, then you'll be able to do okay. And you can sort of extend this kind of principle to higher order intersections. by taking this notion of summation minus union and doing sort of higher order inclusion exclusion to figure out what's in that set. End up drawing lots of Venn diagrams, but you get the answer eventually. Okay. So, in his exercises, Vickel asked you essentially to follow the following algorithm, follow the following outline. So I'll quickly go over this, but not go into the details, because clearly something you can go through the exercise and work out yourselves. It's a really nice observation, really nice results that I think has sort of been missing for a long time, that says, look at K-limit values which we're computing with bounded independence. Can we again estimate the cardinality or the fraction of a particular subset of elements that we've seen, right? So in other words, we saw some observed set of data. I built some summary, and then after the fact, someone comes along and say, well, what fraction of elements from the original data fell into some arbitrary subset? Okay. So, if I knew that arbitrary subset up front, I would just count those elements as I saw them and get my answer. But if this is going to come along later and maybe be dynamic, I'll start answering one kind of question and answering another kind of question. I don't have that advantage. I need to instead be able to answer that kind of question after the fact. So the natural algorithm is sort of the thing I talked about yesterday, right? Run your summary to get some sample set to call K, and then just look at, here I switch back from T to K, just look at the fraction of elements in your sample that meet this criteria, that are in this set A, and use that as your estimate for the global sample, for the global fraction. So again, we want to think about how do we analyze this, understand this under limited independence. And the trick is really very, very neat. It says, let's actually think again about what's the chance that we overestimate, what's the chance that we underestimate, down the probability of each of those, and argue that there's good constant probability that we'll get something that's neither an overestimate nor an underestimate. So the difficult thing here is that before we were just looking at what's the probability of elements sort of hashing within a certain range. Now, actually, we have two things going on. We have what's the probability that we have maybe too many elements hashing in this target range, or what's the probability that we have, say, too few elements from the target subset A hashing into this range. And either one of those can kind of push us in the wrong direction. So what we can do, though, is just sort of essentially pick some middle point and say, let's argue that we're unlikely to have too few elements from the original input hashed below some threshold, and we're unlikely simultaneously to have too many elements from the target sample set hashed below that threshold. And then say that if neither of those happen, then we won't have, in this case, an overestimate. So take that one sort of compound event of having a bad estimate and break it down into events based on the original set and based on the target subset, reason about those independently, and again bound the overall probability of failure by union bound. And once you've done that sort of breaking down the compound event into some events, then we can go back to the kind of techniques we're familiar with, reason about the probability of this event using the Chebyshev inequality and the pairwise independence of the hash functions to analyze the probability of each of these, and then just sort of combine them all together. So we bound the probability of an overestimate up to some constant, bound the probability of an underestimate up to some constant, and then argue that these constants still added together are small enough that we're unlikely to be in either of those bad cases. So constant probability of success. And again, so what you'll do is you'll repeat and again take median following this outline that we've seen before. And then it's just a question of, again, setting parameters to say what kind of guarantee do you want to give. Right? And again, you'll realize that if you want to give a relative error guarantee on this fraction, what fraction of people are in the subset, this is going to be hard because, again, that fraction can be very small. So you'd need to sort of sample almost everything to get it accurately. So you'll choose exactly how to give the guarantee, right? You might say, well, let's just assume some lower bound on this fraction. Assume some lower bound f prime on this fraction. Then say, well, I'll get relative error epsilon at everything that is at least this fraction by setting k the number of elements that I'm keeping proportional to this fraction f prime divided by epsilon squared. Any questions on this?
Is there a lower bound, the accuracy and the space you need to approximate the intersection of two subsets?
Yes. Okay. So the question is there some lower bound on, in your case, the question of estimating the size of the intersection of two subsets, or many of these other things? So the answer is yes. There's a whole line of work on lower bounds. And in fact, intersection of two sets is one of the sort of the fundamentally hard problems here. So, in your algorithms and complexity class, you see, the theory of NP completeness. You see that there are these sort of basic fundamentally hard problems, and if you can reduce, your problem to one of these hard problems, then you can argue that it's in the same hardness class. So the same is true in these kind of cases. The problems are different, but the problem of finding the intersection size of two sets in small space, or really solving a communication game where two players each have a set and want to see if the intersection of those two sets is empty or non-empty, is again one of the fundamentally hard problems that says in order to do this, even with allowing randomization, you need space proportional to the size of those sets. So that's sort of the underlying reason why, right? That says why we can't have relative error for all possible things, because we're just not going to be able to break that lower bound. And that then has implications for the size of summaries for a lot of other problems. There's a very different hard problem that we use to say also that just estimating unforeseen elements requires 1 over x squared space. And again, I think that's the gap Hamming distance problem, which is one about saying you have two strings and you're given a promise that either their Hamming distance is just below a threshold or just above a threshold, and you have to, with a sort of a gap between the two thresholds, you have to determine which case you're in. And again, that requires a certain amount of space to solve, which implies a lower bound for these things. So there's a whole sort of line of work on lower bounds for these summaries, which I think I have some notes in the slides, but I probably won't get to in detail today. So where have we got to? We've got to this idea that hashing is a powerful technique that lets us create summaries, and we can then reason about the accuracy of these summaries and update these summaries in streaming settings. And what have we built so far? We've seen results that say we can test equality using fingerprints. We could recover approximate entries using either the count min sketch or the variation I talked about, count sketch, based on the AMS sketch. We can estimate things like Euclidean norm and dot product between vectors. We can estimate the number of non-zero entries and subset sizes, and things like Bloom filter also give us approximate set membership. So I have a lot of other topics, and I'm going to pick just one or two to talk about next. So one thing I think that's interesting and sort of follows on from the things we've seen already, this idea of LP sampling, and particular L0 sampling. So what we want to do here is use sketching and hashing techniques to help us sample. So we've seen coordinated sampling techniques that work when we have uniform inputs and work when we have weighted inputs. The twist here is we want to accommodate the case where our inputs change the weights incrementally over time. So now I have that scenario I explained yesterday, arrivals and departures, where each update in a stream tells me an adjustment to the weight of an element. And I want to, that's going to then give me a vector of weights of elements, and I want to sample based on some function of that vector of weights. Right. So I might want to sort of just sample from the support set of that vector of weights, so sample from the elements that have non-zero frequency after all the arrivals and departures. You might want to say sample proportional to the absolute weights in that frequency vector, or some other function of the weights, say proportional to the square of the weights. So how do we do this sampling effectively? Well, this idea came up fairly recently of a range of techniques that will allow us to do this. So what this says is that we have some input that defines a frequency vector f, and we want to sample the ith element of this frequency vector with probability proportional to the pth powers of that element, scaled by the sum of the pth powers. Doing that exactly is going to be difficult, so we're going to tolerate, again, some approximation. We're going to say, well, I'll give you a little bit of wiggle room. You can some elements can be slightly more likely than that probability. Some elements can be slightly less likely than that probability. That's going to be fine. And it wasn't clear that such things would exist. We said, well, if we had such sampling schemes, then we could solve these problems, but it wasn't clear until a few years ago that actually you can build sampling schemes based on these sampling probabilities. The first result came out in about 2010 with some improvements a year later. And these have some interesting applications. So what I'm going to do is I'm going to talk about L0 sampling and then say how it allows us to do graph sketching. So moving from this, so far we've been looking at the setting where everything we see we can think of just as a vector. I'm going to show some application where we can now start thinking about something more complicated in the form of a graph. Okay. So the technique I'm going to focus on is this idea of L0 sampling. So L0 sampling says we want to sample proportional to fi to the power 0 divided by f0. Okay, so that's a slightly using notation to say really we just want to sample from those elements that have non-zero frequency. So I may see many elements arrive and depart, leaving me with only a small number remaining, and I just want to sample uniformly from those that remain. And that's sort of where things are tricky, right? If I only have arrivals, if I only have positive arrivals of elements, then things like K-minimum values and coordinated sampling will let me do that sampling directly. When I have departures, so I may say something that then goes away, that's when I need some extra power. And I'll show you with the graph sketching example that this is actually something useful for a particular application. So it turns out there's a fairly sort of general approach that works here. Right? And the idea is really I'm going to sort of, if I knew, what kind of thing could I do? Well, if I had very few elements left at the end, so I see a lot of arrivals and departures at the end, I only have a small subset remaining, then what I could do is use something like the invertible Bloom lookup tables to recover that set of elements, and then just sample from within those. If I have a very large number of elements remaining at the end, I just want to say, well, notionally, I want to sort of put those through a filter. So I would sort of randomly select, using a hash function to be consistent, a subset of those elements to go into something like an invertible Bloom lookup table, recover a small set, and again sample from those. So the difficulty is I don't know whether I'm going to be in a situation where I have a very small number of elements surviving, or a very large number of elements surviving, or something in between. So, like a good computer scientist, I'll just make all possible guesses simultaneously and see which ones work out. Right? So what I mean is, I'll pick some probability P and sort of use this P to subsample, or almost like filter, the items that I see. So, based on a hash function with probability P, some item will either pass and go into some subsequent data structure, or it will fail and be ignored. So this generates some subsample vector frequencies, which I'm denoting by the vector f subscript p based on the probability p. What we'll actually do is we need something slightly stronger than the invertible Bloom lookup table. We need something which I'll call case fast recovery. And I'll explain exactly what that is and how to build one. But basically a case fast recovery data structure says that if my vector has a small number of distinct elements in it, then I can recover that vector exactly. Okay. So I can sort of reconstruct this vector fp, provided it has small support. If it has large support, my data structure will just say, fail, can't do this. Okay. So if I picked p correctly, then I've kind of subsampled my input vector down to a point where I can recover, and from that recovered vector, I can then just sample an element that I want. And I said, well, what I'll do is I'll just, guess all possible values in parallel. What I mean is, in parallel, I'll pick p equals 1, p equals half, p equals a quarter, down to p equals 1 over n, roughly. So hopefully this is clearer with the picture. I have my input, which I'm sort of saying, I think of as a set of items as a collection of coloured dots. With probability p equals 1, they all pass through the filter and go into some case fast recovery algorithm. Then with probability half, some of them come through the filter and go into an independent copy of a case fast recovery algorithm, probability quarter and so on. So at some level in this structure, I should have picked about the right probability that not too many elements pass the filter so that I can recover them, but equally not too few elements pass that I end up with an empty vector. And then I can recover those and do the sampling. So where I need to do a bit of analysis is just to sort of fill in that gap that I said, that I should be able to pick some probability, some level, where there aren't too many elements that survive, but there aren't 0 elements that survive. And that's going to be reasonable because I get to choose what is k, what is the capacity of this case fast recovery algorithm. So again, I'll pick k being moderately large so that there's going to be some level where I succeed. So if n, or shorthand for f0, the number of distinct elements in the original vector, then at any given level p, the expected number of elements that survive, that are selected into this thing, fixing that vector now, just fix the final vector after the screen, will be n times probability p. And I'm going to be reasonably happy so long as I pick a level p of value of p, so that between, let's say, 1/3 and 2/3 of the elements actually make it through. Right? So what I mean is I have my expectation, and I want to say, well, I'm within sort of, say, half my expectation and twice my expectation. The bad event is I get 0 or I get more than k. And this is something where I can apply a Chernoff bound. If you're paying attention here, you'll sort of say, well, what's going on? Because if I'm using a hash function to decide this sampling probability, what independence do I need in my hash function to apply a Chernoff bound, which is to assume full independence? The answer is, actually, I can use sort of a modified Chernoff bound using limited independence to get this result. I can pick this parameter k, what is the size of the sparse recovery that I want to support, to be, say, logarithmic in 1 over delta to get a a 1 minus delta probability of success. So what that says is the general outline is fairly clear. I'm going to repeat this process with different probabilities P of passing elements, feed the result into some sparse recovery algorithm, but I need to do some steps in the analysis just to argue that, for example, I will succeed, that there'll be some level where things work out for me. The next question is, how do I actually do this sparse recovery? Right? So I'm almost in the second invertible balloon lookup table. The difference is my elements have a weight associated with them. Right? But the actual outline that I can use to solve this is more or less the same. Right? So a simple outline would be to use some data structure like a counting sketch to summarize that vector. And you would argue that if the vector you're summarizing is not too dense, then actually you can just estimate the counts of each possible element in the universe. You won't get many collisions, and then you'll be able to work out exactly what's going on. That's the problem with that is it's very slow to decode. Essentially, you're trying to decode this vector from this summary data structure. And if you have to sort of just query every possible element in the universe, that's going to take a long time. So what you can do is essentially the same trick that Michael talked about, which is keep some additional information about what's mapped into the cell in a way that is linear, a linear transform of the input again, so that as elements are added in and subtracted out, you're able to update this information. And so that you can then try to decode what is in a cell if it's a unique element. Right? So what we'll keep now in here is something like, say, the sum of elements identifiers, so the sum of element identifiers that map into the cell, the count or the sum of the weights of elements that map into the cell, and some fingerprint of the vector of elements mapping into the cell. And the idea here is if this cell is, say, pure, that is, it has a single element within it, then essentially you can just take the sum and the count, divide the sum of element identifiers, or the weighted sum of element identifiers, by the sum of weights to get the atom identifier. Right? That will not work if you have more than one element mapping into the same cell. So what you can do is simply try to decode a cell, and then check, is the fingerprint of that cell the fingerprint of the element that you've decoded?
What exactly do you denote by xi?
Yeah, so here, xi is sort of the weight associated with index I. So you can think of xi being sort of the weight in the ith entry of the vector.
Okay, but then what is the weight?
What is?
The weight. Can you define the weight?
Okay, yeah. So what I mean here is, going back to this model of streaming data, then our model says our updates are of the form, here is an index and an associated frequency count weight with that. So the weight of an index is the sum over the whole stream of those weights that correspond to that index. So this actually, we should really think of I times xi.
So how do you update the sum? So when a new element comes, how
Yes.
do you know whether it wasn't already there?
Doesn't matter. So what we're doing is we're saying in our cell. So this is sort of the trick, right? Chalk. So when I get an update of the form I the idea is that at the end of it, at the end of this process, if I have a single element in here, then I can just take the sum, say IC, divide by C, get I back out. That's not going to work if I have multiple elements colliding in the same cell, so the fingerprint of that weighted vector will let me check. Okay. So the important thing about this data structure, and an open problem, I guess, is to look at other ways to construct data structures that have this property and fine-tune the constants and so on, is just following this simple outline. We can keep a sketch of size proportional to k, the number of elements we want to decode, times log u, the size of the universe, in bits, to recover up to k items. Skip over that. So when you put that together, we have this black box data structure that lets us do L0 sampling, that lets us sample from this sort of weighted vector elements. So why would we want to do that? When are we going to see a situation when we may have these sort of negative updates? So I'll show you one example that's came along a couple of years ago that I think is really clean and really neat. It says, well, let's think about streaming data. Let's think about streaming data that defines a graph. And we want to understand what are some properties of this graph that we can find out. For example, is this graph connected? How many connected components does it have? And again, if you're looking at data where you only have insertions, arrivals of edges, then this is reasonably straightforward because you just keep track of what are the different components. Initially, everything is in a component of its own. And as you see edges that merge components, you keep track of the current set of components. So this gets interesting when we have edges that may arrive and depart. So what would we do if we had, if we weren't under this sort of streaming setting, but we were just seeing the arrival and departure of edges, and we could keep information about all those edges around? Well, what you do is you'd then say, well, which edges survive at the end? And then you'd run some sort of standard algorithm that says, put everything in a unique component, and then just pick edges, and you contract those edges to merge those components and sort of repeat that. Right? And you can kind of think of this almost as a parallel algorithm where you'd have, say, a logarithmic number of rounds to contract all those edges to get to the final set of components. So what we want to do is essentially run exactly that algorithm, but rather than keep all the edges explicitly in full, of which there may be a large quadratic number of edges, we're going to represent those edges inside sketches, L0 sketches, and use properties of the sketches to essentially let us simulate this algorithm. Okay. So the key step of this algorithm is really at some point you have some collection of partial components, and you want to say, well, pick an edge from each that's going out of each component. Right? Pick an edge that connects one component to another component, contract that edge and say those two components are now one big component together. So what we want to do is use L0 sampling for that step. Use L0 sampling to pick the edge going across components. Okay. So you can kind of imagine just directly using L0 sampling, applying, keeping one L0 sampler for each node, using it to summarize the edges incident on that node, and sampling an edge from each node to sort of get you started. And that will work okay. You'll get an edge incident on each node, you can contract them, you'll end up with some components. And you can kind of keep trying to repeat that process. But you'll find it kind of breaks down after a while, because at some point you will build a large component with many nodes. And if you just look at trying to do a sample of an edge incident on each node, then you're quite likely to pick edges, or you're almost certain to pick edges that are internal in the component. And that doesn't tell you anything new. What you want to do is say, you want to make sure that you're going to pick edges that are going out of that component, connecting to another component. And there may be only one such edge that is going out of this component into another component, and yet somehow you want to be sure you'll pick it. So the real sort of insight and cleverness of this algorithm is it says, well, let's just pick the right kind of encoding of the adjacency matrix to force this to happen. Right? So rather than encode the adjacency matrix as sort of a 1 if there's an edge from I to j, we'll actually either use a +1 or a -1. Right? So what we'll do is we'll sort of fix an ordering of the node IDs and say if node I, the value of node ID I is less than the value of node ID j, then the edge ij will encode as sort of the identity ij and a +1. And we'll also encode that edge for node j, but we'll encode it with the same identifier, but a -1. Right? And the idea here is that when I and j are in different components, and we're sort of sampling, then we may sample the edge ij from I, because it has weight +1. And we may sample the edge ij from node j, because it has weight -1, and both those are non-zero. But if we then decide that I and j are in the same component, either because we sampled this edge or we sampled some other edge that put them together, then what we'll do is we'll say, well, let's build one L0 sketch of all the nodes in the same component by summing up their sketches. So here what we rely on is the fact that these sketches are linear transformations. Right? You can go back and see that everything we did to build the sketch, you can represent as a linear transformation of the input. Okay. So if node I and node j are in the same component, we've added their sketches together, then for the identifier ij, meaning edge ij, we have a +1 contribution to its weight coming from node I, from the sketch of node I, and -1 contribution to its weight coming from the node j. So it exactly cancels out. So what you can see is when you do this sort of summation, the contribution to the weight from every internal edge in the component goes to 0. And what you're left with is just contributions to the sketch from edges that are not currently internal to that component. So the cleverness here is sort of twofold. One is designing and using these L0 sampling algorithms for this problem, but secondarily sort of come out with the right way of encoding the input so that when you combine these sketches, things that you don't care about kind of disappear and things that you do care about remain. So we end up with only sort of edges not internal to the current set of components are represented with non-zero weighting sketches, so we can sample them, and then it's just a case of saying that, how does this all work in terms of independence? Right. And then the argument says, well, we're going to, even if there's sort of one enormous component of size roughly proportional to the number of vertices, it's going to contract in size sort of every round. So we only need a logarithmic number of rounds of repetitions of this edge contraction to get down, and we can essentially use fresh sketches for each round. Right? We can have a logarithmic number of sketches, the first one for round 1, the second one for round 2, so that we don't, and the reason for that is that you always have the concern, how is the independence working? We need to always be worried about, well, am I actually conditioning what I'm doing now on some choices that I made earlier, and so I'm losing independence. If I have independent sketches with independent random values used to make them, then I can more easily make the argument that says that what I do now, even though it's conditioned on what I did earlier, is still independent of that. So I'm not worried, right? So what I mean by that is what could go wrong here, right? So one thing you might be tempted to do is take an L0 sketch and say, let's sample some element from that L0 sketch. I get something out. I might say, well, this sketch is linear, so let me subtract this element off the sketch, and now that's gone. Let me sample something else from this sketch, and I get something else out. Let me subtract that off, and keep repeating. Right? And And this would be something of a contradiction, because if that really worked, it would say I could summarize a large, let's say n elements inside an L0 sketch, and I could somehow recover them. So that can't be true if my sketch is very small. So the reason that kind of technique will break is because I'm conditioning my actions on the sketch on things that I've learned from it. So, all the arguments that work about the probability of success will break down. So, you can view these sketches as black boxes, you can sort of interrogate them in various ways, but you still have to remember the rules of the game. You can't do things you can't do new operations on them conditioned on what you've done before without reasoning carefully about how does that impact the independence and the probability of success. Okay, so, we're not going to break any information theoretic lower bounds here with these kind of techniques. So going back to the graph sketching, what do you get when you put all this together? You get that you need a logarithmic number of sketches. You need one sketch for every node. So, for n nodes, you're looking at a total space of n polylog n to implement this, compared to being able to store, say, a quadratic amount of space. So it says in sort of this sublinear in the potential total size of the graph, you can track things like connectivity. It turns out there's a few other things you can do. You can do things like k-connectivity. You can look at things like whether a graph is bipartite or not. You can look at what's the weight of a minimum spanning tree, using sort of variations of these ideas. So the big picture here is to say, we can build these kind of sketch techniques, we can understand them in the context of vectors, and then we can start to apply them to other kinds of objects, other kind of more complicated objects, like graphs or matrices. So the other thing I want to talk about today, skipping all this technical stuff, is some basic results for using sketches with matrices. Again, most of the sketch results we've seen so far are about saying, what can I do with a vector? Can I summarize, the number of distinct elements in data I can represent as a vector? Can I capture, say, the inner products of two vectors? Well, vectors are all right, but where the real action is in matrices, right? I'm looking at all my customers and how many different ads they've viewed from different advertisers. Right? I'm interested in that matrix of customers to ads, and I want to start reasoning about various algebraic properties of that. I want to do, principal components analysis on that huge matrix. So what I'd like to do is use sketches, use these hashing techniques to help me understand what kind of linear algebra can I do on massive matrices. So what I'll do is give sort of just a sampling of things and a couple of pointers to the kind of things we can do there. So what's the most basic question you might ask over matrices? I'd say it's probably just, can I compute the product of two matrices? So what's the model? The model is, I have two very large matrices that are maybe defined incrementally by a stream. So again, each stream update is going to tell me something about a particular entry of a particular matrix. And what I want to do is approximate somehow this product between these two matrices without keeping the full information about each matrix entirely. So I want to come up with some approximation C, and I want to argue that this approximate answer to this matrix product question is reasonably good. What's reasonably good? Well, I'll look at what's the difference between my answer C and the true answer, AB. And I could try and do this over a variety of different matrix norms. And for convenience, and because it kind of fits most naturally with the kind of techniques we've developed so far, we'll use the Frobenius Norm. Okay. Frobenius Norm says, Frobenius Norm of a vector is just sum up the squares of the entries of the vectors and take the square root of that sum. So it's sort of the natural generalization of the Euclidean norm, or an entry-wise norm, to a matrix. And there's a clear reason of convenience here, which is that the kind of guarantees we get from sketches that we know about already are in terms of sums of squares of elements. So it's likely that these will translate to matrices. So I claim actually that using the sketches we've built so far, we can get some kind of result for this question. And then it's just a question of can we sort of refine this. Okay. So what I can do is say, let me build a sketch for every row of matrix A and a sketch for every column of matrix B. Okay. So I go from very wide rows and possibly very tall columns to just a compact sketch for each. And then I can say, well, look at some particular entry of the output product C, say the ij entry of that output, and say, well, this, I know that, just from basic linear algebra, this quantity is just the inner product of the ith row of A and the jth column of B. Okay. Well, sketches will let me do that. Right? I have sketches, and we argued yesterday that I can simply take a sketch of one vector, a sketch of another vector, combine them to get an estimate of the inner product. But I get this error term, and we said yesterday, we get this possibly quite large error term that looks like epsilon times the Euclidean norm of that row times the Euclidean norm of that column. So this seems a little bit worrying because just for a single entry, I'm getting some error here. So I don't know if this is a trick or not, but really the argument is just to say, well, in terms of what I was trying to get, in terms of making a guarantee in terms of the Frobenius norm, things work out just fine. Right? Because if I look at this error and I sort of square this error over all entries in the matrix, then I can just say, well, what am I doing? I'm summing over all entries ij of that row norm squared times that column norm squared. When I add that up, what I get is an error in terms of the product of the Frobenius norms of the two input matrices. So the Frobenius norm of the product, I can state in terms of the product of the Frobenius norms of two input matrices. So actually, even to get that, I need to be a little bit careful, because that error term that I got for a single entry, I got with some probability delta. Now I want that error to hold for every single entry of the matrix simultaneously. So what I'll do is I'll just say, well, let's just make that probability of getting a bad estimate delta very small, so that when I add up all these estimates, then the probability that all of them are good is still quite small by union bound. So I just make this error probability polynomially smaller in the size of the output matrix. What I remember is the cost of improving the probability of an estimate is quite cheap, right? We depend logarithmically on this failure probability 1 over delta. So I can just rescale delta by something polynomial in n, and it just bumps up my overall cost by logarithmic factors. Okay. So that says that sort of you can get a result of this form almost just by taking things that you know how to do already. So the question will be, how can you do something a bit less naive than this, get something a little bit better? So the first observation is that we shouldn't be so pessimistic, right? Essentially what we did is we said, well, we have this sort of concentration bound on the error in a sketch, and we just said, well, we're sort of within this error bound with constant probability, so let's just make that probability really small and add these up, assuming the worst case. But things shouldn't be so pessimistic because, the errors that we get are random, and they're sort of zero biased, and they're symmetric. So actually, some of the times, some of my estimates will be sort of a little bit high, some of them a little bit low. Things should sort of even out, roughly speaking. So what we can do is say, well, what is our overall error? We can sort of look at a single variable for the overall error of our estimate of the product of the final sketch. of the final matrix product. And you can argue that the overall estimate error is something whose error you can bound. You can look at it through, Chebyshev inequality. So you can say essentially what you do. What I'm sort of saying here is rather than look at each entry individually, look at get a different estimate for this matrix C from different repetitions of the sketching process. Look at the overall sort of summation of the absolute errors, or absolute squared errors for each of these, and I'll look at reason about the random variable that captures this error. And you can show that this random variable, is reasonably well behaved, has good variance. So the temptation is to say, we'll just apply the Chebyshev inequality, follow this Chernoff bounds argument that we've done before. So where this breaks down is that before we did this Chernoff bounds argument to say, well, we've got a bunch of different estimates. Let's take the median of those estimates and argue that things there aren't too many high errors, there aren't too many low errors, so we're likely to be good. The problem here is that we're looking at a matrix. So our estimate is no longer a single value that we can take the median of, but it's a whole matrix. So how do we amplify the probability of the correctness? In other words, we have a bunch of estimates. We know that probably some of them are good and a few of them are bad. But how do we pick which are the good ones? So what you can do is essentially try and generalize this by looking at the difference between all these matrices. So what you can do is say, well, let's just estimate what should this error term look like. Right? So let's call this error term D, being this product of Frobenius norms for the matrices. And what we'll say is we'll look at sort of a notion of median applied to matrices to say, well, we'll find some matrix from this estimation that's closer than half this distance to more than half of the rest. Right, what that says is we're sort of looking for one matrix that's quite similar to a majority of the other matrices, and that's one that should be good, a good estimate overall. Few more minutes. I just want to quickly mention a very nice result of Rasmus in this general area. So the previous discussion was to say, can we sort of estimate the whole product matrix? And we can do that by looking at sort of products and sketches. So another question would be, can we just say which are the significant entries in the product matrix? Right? So these two matrices might be capturing some sort of information about elements such that their product says that there's something interesting happening in this sort of combination of entities from one location and another. Okay. So can we essentially look at matrix A, look at matrix B, combine some summary of those to get some summary of the product AB? So ideally what we'd like to do is sort of build a sketch of A, build a sketch of B, and compute something that looks like a sketch of AB. What we can do is something similar to that, but to do that what we need to do is kind of dive into the structure of sketches. Right? So the first matrix result sort of said, well, we can get some kind of result just by using sketches of black box. Here what we're going to say is to really get the result, we need to really understand what's going on inside the sketches and kind of use the structure that's there and also kind of make some modifications to the sketch that will work in our favour. So let's go back to this kind of sketch construction. So we think of saying, well, we have some entry in the sketch, in a sketch of the product AB that we want to be sort of mapped as a function of index I and index J of this entry to some cell, and we're going to keep some information about the weight of that entry in that cell. And what we require using the count sketch idea is that each entry of the product should be mapped by a pairwise hash function to some cell in the sketch. So, there's a number of ideas we need here. So one idea is to say, well, can we choose a hash function that has a bit more structure to it? So in particular, can we choose a hash? We can argue that we can choose a hash function of this pair ij that is actually composed of a hash function on I and a hash function on j. Right? We can argue sort of roughly similar to sort of the tabulation hashing argument if this is pairwise independent. Right? Two elements ij, two pairs ij and I prime j prime must differ on at least one coordinate, and so based on the hash value of that one coordinate where they differ, we'll argue that they're pairwise independent. So what we'll do is, rather than take a sketch of the whole of matrix A and the whole of matrix B, let's just look at, in this case, column K of matrix A and row K of matrix B. And what we'll do is we'll take the convolution of those two sketches, right? The combination of inner products of all shifts. So the reason for doing this is really this observation about matrix product, that we can express matrix product in terms of summation of outer products. And then it's really just sort of an observation about the polynomial structure of these sketches that says that this convolution of the two sketches of a column and a row captures all combinations, right? I get every combination of entries from that row and from that column expressed somewhere in this convolution. I get things ending up sort of exactly where I want them. So roughly speaking, if I take the convolution of these two sketches, I get a sketch of the outer product. Once I have that sketch of the outer product, then that's the sketch of the kth outer product. So I sum this up over all n different outer products, and I end up with a sketch of the matrix product. So convolution is a nice operation to use because I can do it quickly using fast Fourier transform. And moreover, I'm taking the convolution of sketches, so I'm using something that's proportional to the size of the sketch rather than something that's proportional to the size of the matrix. Each sketch convolution gives me a sketch of the kth outer product. So I take n outer products. In each outer product, I look at n entries in the corresponding row and column and do this, sketch those and then do the convolution. So what I'm getting up with is a sketch of the matrix product much more quickly than if I actually ran even the fastest matrix product algorithm and then took a sketch of that. And the error in my estimate I can reason about and I can bound in terms of the size of the sketch that I'm using. I think this is really nice because it kind of brings together a lot of different observations. It says, okay, we need to understand how the hash functions work and how we get the amount of independence that we need for the hashing into cells. It requires sort of understanding the structure of the linear algebra operation that we're doing and the fact that we can express this in the right way as a sum of outer products, and that essentially that this operation on sketches, this convolution operation on sketches, gives us exactly what we need to get that sketch for outer product. So where's all this going? So I said we can do matrix multiplication by looking at a combination of sketches to get an overall estimate of the matrix product. We can also do this compressed multiplication to pull out sort of significant entries. There's more recent work that also looks at matrix multiplication, saying how do we get this sort of more directly? How do we optimize the log factors, but the overall error bounds are roughly of the same form. So the other kind of things you might want to do is say, well, what other linear algebraic operations can you do? Right? Can you do sort of linear regression? Right? Given a matrix A and a vector B, can you find some other vector x that approximately minimizes the difference between ax and b? And so the natural thing to do, well, somewhat natural, I guess, is say, well, rather than, if we want to use sketches, then let's do exactly that optimization, do exactly that minimization, but in a sketch space rather than in the original space. In other words, we'll sketch the matrix, and we'll sketch this target vector B, and then we'll sort of find some X in the sketch space that minimizes this, and argue that we can sort of map that back into the original space. But again, actually doing that requires understanding a lot more of the geometry of what happens when you're within sort of some sketch space, in order to be able to sort of reason about the overall accuracy of the result that you get. So I want to kind of wrap things up now, and sort of take a look back at what are some of all the things that we can do here. So in terms of using hashing techniques and building summaries over streams of data, there's actually quite a lot of things that we can do, right? We can do vector equality using fingerprints. We can pull out estimates of elements in a large vector using count_min and count_sketch. We can estimate Euclidean norm and inner products of vectors using AMS sketch and using Johnson-Lindenstrauss lemma implementations. We can estimate counts of distinct elements, or F0, using count_distinct KMV, K-minimum value sketches, hyperloglog. We can do L0 sampling. We can do sort of matrix summarization, and a whole bunch of other stuff that I didn't have time to talk about. As we mentioned briefly, there's a lot of lower bounds here as well, a lot of work on lower bounds of proving what's the limit of what you can do, based on sort of communication complexity and sort of fundamental hard problems in that setting. And there's a lot of more advanced work going on that sort of starts from these results and goes even further. So more generally, there's this whole area of research into sparse representations of high-dimensional objects. Right, so I mentioned compressed sensing yesterday as one area. Another big area right now is this notion of a fast Fourier transform. So if you have signals, a signal such that its Fourier transform is sparse, meaning that there's only a few significant entries in that Fourier transform, can you do some kind of sketching technique to pull out those significant entries in the Fourier transform? The answer is yes, and sort of the surprising thing is that this is something you can do in this sketching world even faster than actually running the fast Fourier transform. I mentioned sort of matrices. Again, big matrices are where there's a lot of interest, because a lot of this sort of big data you can think of as being represented by big matrices. And again, I mentioned, people looking at linear regression. We're also trying to figure out how do you do things like SVD, find out the eigenvalues, find out the best K-rank approximation of a very large matrix using summarization and sketching techniques. We want to look at lots of computations on graphs. I sort of said, well, some very basic things like you can track, you can identify what are the connected components, you can estimate things like the weight of the minimum spanning tree. But you like to do much more sort of complex, say, spectral things over graphs. So can you sparsify your graph? Can you sort of do a clustering on a graph or a matching on a graph using only a compact summary of the information in that graph? Alex is talking a little bit about sort of high-dimensional geometry, but again, lots of sort of basic geometric questions we want to understand in terms of, can we solve optimization problems over geometric data? And this leads into sort of machine learning, because a lot of machine learning is really about viewing high-dimensional data in a sort of a geometric way and identifying structure, identifying patterns within that data. And another thing to be aware of is it's sometimes sort of thought that all of these problems go away if you just build a cluster with enough thousands of machines and throw enough CPU cycles at it. But that really isn't the case, because most of the interesting computations that we want to do are things where we don't really know good parallel MapReduce style algorithms for them. One of the neat things about these summaries is that they take functions that seem sort of very centralized, very sort of single CPU style, and actually break them up. You know, as soon as you have something that's a linear transformation of your input, then you can sort of break the input into different pieces, compute the linear transformation of each piece separately on a different machine, then bring those summaries back together to combine them and then estimate your answer. So rather than thinking of a sort of summarization of something in opposition to distributed computation, we can really think of it as something that complements and goes hand in hand with distributed computation. So sort of putting these things into MapReduce or other distributed models is a topic of significant interest. Okay. So I know you're all waiting with bated breath for the exercises that accompany this talk. So I'll just hand these out. Similar in style to sort of Michael Mitsemacher's exercises. These are sort of very much sort of a few questions to contemplate. Pick one or two and sort of think about it. I'm afraid these aren't quite as nice in walking you through the solutions as some of the other exercises. So that is probably a good point to pause and reload on coffee. So I will thank you for your attention and ask if there are any more questions.